the problem. Okay? So let's go through this code and see how it corrects that. So it again initializes the connections to 0. You see what it does? Before it increments, it checks whether connections is less than 5. That's the problem here. It doesn't check what is the current value of connections. It keeps on incrementing, and then to decide whether to grant or deny access, it checks whether connections is less than 5 or else, right? But here, it checks, to increment itself, it checks whether connections is less than 5. Because you are not supposed to increment if connections is greater than 5 or equal to 5, right? Because that's what happened. If you keep on incrementing, someone can generate all those fake connection requests and just keep incrementing the connections and make it to overflow and come back to 0, and someone can arbitrarily get the connection request granted. Whereas here, if you see, once connections becomes what? It allow connections 1, right? Because the first connection request will be incremented from 0 to 1. So the first connection request will be allowed, second will be allowed, third will be allowed, fourth will be allowed. Okay? When connections is 4 less than 5, right? For the fourth connection request, what happens? Let's do one by one. If connections is 0, someone requests the first time, 0 less than 5, right? Then you increment connections from 0 to 1, right? So connections becomes 1, and 1 less than 5, you grant the access. Okay? Then the second one, connections is 1. For second connection request, 1 less than 5, 1 plus 1 is 2. So connections is 2 less than 5, grant the access. So that's for the second connection request. For the third connection request, come over here, 2 less than 5, true. So 2 plus 1 is 3. So connections is 3 less than 5, you grant the access, right? Then the fourth connection request, connections is 3 less than 5, 3 plus 1 is 4 less than 5, you can grant the access. Now, for the fifth connection request, connections is already 4 less than 5, it is true. So increment connections from 4 to 5, so connections is 5. But 5 is less than 5. Is that true or false?
No, it's
false.
not.
So you don't grant access, you deny access. So once connections becomes 5, right, for the sixth connection request, what happens? You check whether connections is 5 less than 5. 5 less than 5 is false. So you don't go inside and increment connections, right? So connection stays at 5. And as long as it is less than, greater than or equal to 5, you are not going to grant the access, right? Connections now is at 5. So for every subsequent connection request, it stays at 5. Okay? It doesn't get incremented. And because it is 5 is less than 5, not true. So you don't give or grant access, you always deny access. So the program corrects this problem by making sure the connections variable is not incremented for every fake connection request. So someone can keep on generating connection requests. Once it reaches 5, it's not going to get incremented because 5 less than 5 will always become false, right? So it's not going to increment connections beyond 5. Okay? So that's how it fixes the problem. So even though it looks like the genuine program here, you see the vulnerability that could be introduced because of oversight or lack of analysis of your code. Okay? Here. And that's what I have described here. We'll move on to the another overflow attack called the buffer overflow attack. Now, this is kind of a buffer would be what, something that can hold something, and if, for example, I have right here, if you have like a 4-liter jar, 2-liter jar, and you have 4 liters of water, right? If you pour more than 2 liters of water, it's going to overflow. Isn't it? Common sense. So if you have, say, an array that can hold so many characters, if you're going to write more than that many characters, it's going to do what?
Overflow.
It's going to overflow, but in this sense, overflow will be what? It will write to the subsequent memory locations. So you know, things are stored in memory, right? So this is a buffer that is stored in memory. And you know, memory is linear. Linear means what? The memory addresses increases linearly. Okay? So if you have again taken architecture course, you know that structured bit quantities or 64-bit memory addresses, you can say this is a low memory end, this is a high memory end. What I mean by that, it means the memory addresses could be listed in an increasing order. Okay? You have a structured bit quantity memory address, you can list list all the memory addresses in increasing order. Okay? So I can say this is a low memory end and this is a high memory end. So as I fill things, if I try to store more than what the buffer can handle, I'm going to override the subsequent memory locations, right? So as I showed here in an example, if you have an array of 10 characters, right? If you create a character array that can handle only, that can store only 10 characters, and if I have a for loop that is written like this, okay, and say sample of I equals some a. What is that? Is this a not? Is it right? Is anything wrong with this code, or everything is fine?
You start at
I is
0.
less than equal to 10. You should be I is less than 10.
Yes, we have something.
Yes, same.
Okay. Why? Because array index starts from 0, right? Normal any C, C++ Java, unless you work on Pascal, I don't know about that. But, so this is 0, the valid index values are 0 through 9. Alright? So here you're trying to do what? 0, 1, 2 up to 10. So you're trying to store the 11th element into that array. So it's going to try to write to the subsequent memory location in the array. Okay? So that is what we mean by buffer overflow. Right? So what happens? When you write a subsequent memory location, whatever the variable you have there, if you have a big program, right, that's what we're going to see after this, that other variable is going to be affected, right? If you store something else over here, it's going to be, its value is going to change, right? Isn't it? Sometimes, especially when you work on C or C++, you will get what? A segmentation fault. And one reason why you could get a segmentation fault is this. Because sometime back we saw that the memory is allocated for user programs and operating systems, right? So you work mainly in the space allocated for user programs. And one of your programs does like this, writing out of the buffer. And if it writes to a memory location that is not supposed to be accessed by user level program, that's when you could get a segmentation fault. Because you're trying to access a memory location which is not accessible. Okay. So here I have a kind of couple of variables, a string buffer A, which is 5 bytes long, and integer, which is 2 bytes, even though integers are typically 4 bytes. We just consider 2-byte integer. Okay. And this A, the string is initialized with null or just say 0, so this is just all blank, all zeros. Okay. and the integer is basically 4. Okay? The numerical value of it is 4. Now this also leads you to know about what is called, so before we work through that, we need to know what is called a big Indian system and little Indian system. So can anyone tell what is the difference between a big Indian and little Indian system?
Big Indian starts from the big end. Little Indians start from the little end. It's basically which way you read the bits.
Right, which way you read the bits, almost. So again, as I said, memory is linearly ordered, right? You can go from low to high. Okay. So let's take up a byte. Okay. So let's say, for example, you want to represent 140. Okay. We know 140 in binary is going to be represented like this, right? We just did that, isn't it?
Mm-hmm.
This is what it is, right? But how do I store it in memory? It depends whether it's a big Indian or little Indian system, right? If it is a big Indian system, okay, if this is 140, right? If it is a big Indian system, the most significant bit is at the low memory end. Okay? So which means this 128 really goes here. So let me write like this. So this is the low memory end. So this is 128 and this is the high memory end. So this is your 1. Okay? So the least significant bits goes to the high end and the most significant bit goes at the low memory end. Yes?
What do you mean by high memory end and low memory end?
As I said, memory addresses are linearly, you can order.
Just the address. Okay.
Right. So if your memory address is like 32-bit address, like you can start with this and then you can say this is my memory address, second memory address, third memory address and so on. Right? So you can linearly order. Right? So if it's a big Indian system, I put my most significant bit in the low memory end. Okay? So, and then my other bits go like this. 32 will be this. So this is something very important you should know to understand some of the topics from now on. Okay? So this is how you store things in a big Indian architecture. Okay? And if you want to represent it in a little Indian architecture, it's the other way. What is that?
The most significant bit starts on the high end.
Right. So in a little Indian architecture, the least significant bit starts at the low end, or is at the low end, so it is stored like this. Okay. So this 1 goes here, 0, 0, 1, 1, 0, 0. Okay, so you can store it in 2 ways. This is what it is. You can store the most significant bit in the big low memory end or in the high memory end, right? So how to remember this? I can give one clue. Little Indian, the least significant bit goes at the low memory end. So all else. For Little Indian, the least significant bit goes at the low memory end. And once you can remember that, the other big Indian is the opposite. The least significant bit goes at the high memory end. Okay? Or the other way is the big fat guy, 128, goes at the low end, right? In big Indian. So the most significant bit goes at the low memory end. Well, that's probably difficult to remember. So always go with else. Little Indian, least significant bit, low memory end. Okay? Alright. So let's see if we have still time. This is something you guys have to know. Okay, work through this and see whether you can understand it. I have explained it in the example and we will continue next class, and also the following 2 examples. So make sure you practice this before you come so you can understand more easily as we do it in class.
So the quiz will be here?
The quiz will be here on Wednesday, so we'll start with the